All right, I'm going to start my presentation. Before I do that, again, I want to thank the organizers, National Rural Infrastructure Development Agency, Ministry of Rural Development, Government of India, for uh, giving me this invitation to attend international conference on new technologies and innovations in rural roads. I wish I'm there in presence, but I know this is a difficult, but I will, hope to visit in the future and then give this talk in person. I also wish the conference committees and also conference organizers to have a successful conference. So with that, let me go with my topic. And before I do that, I also want to mention that at the Transportation Research Board in US, I've been involved with Low Volume Road Conference for several years. So I'm so thankful that we are doing this in India. So hopefully we'll have something, a bigger conference down the line. And, I will have a more involvement from US participation as well. So this is the title of my topic, Sustainable Stabilization Methods on Low Volume Roads. I will briefly go over the stabilization aspects, and this is the background of my geotech, and this is an important part of a nice low volume road to perform as per the design. I'd like to acknowledge several of my collaborators, my PhD students and former postdocs, starting with Dr. Congress, Dr. Chakraborty, Dr. Biswas, Dr. Thomas, Dr. Chaluri, Dr. Zhang, and Dr. Vempati. Many others. They all played a big role in this research works that we had done both at the University of Texas at Arlington and at my current university, Texas A&M Civil Engineering Department. Basically, the outline of my presentation is on these topics. I really will start with the talk about the problematic soils. I focus more on sulfate soils. So if you see on the road that what you see is just a Las Vegas, it's a Stewart Avenue road. It's a low volume city road. And this road after stabilization and then building of the top section started heaving, and then you see the amount of cracking. All this is due to the sulfates that are present in the soils and where upon they stabilize with the lime treatment. So there's chemical treatment actually called heaving, and that is what we call sulfate heaving. So after that, the introduction of sulfate soils, I'll go briefly into sulfate heaving mechanisms, and then I talk a little bit of case studies, and then how can we stabilize with the better methods. And then I will also cover a little bit about sustainability, and then I'll conclude in the end. So most of us know natural expansive soils, which we have plenty in India, black cotton soils. And the thing, there's another one of expansive soil, but it's a man-made, which we call it as sulfate soils. So these sulfate soils, when you treat with the lime, they start forming this ettringite, which is again a heaving mineral and causes significant heaving. And 1986 lecture, Dr. Jim Mitchell has talked about it. Then so much work has been done since then. Been involved in many projects in the US as well. And this is again not just one or two places. There's several countries that have been dealing with, including in India. We have several projects, and again, in US also several states identified this as a big problem. So this is the map. On the left side, what you see is an expansive soil formations. The red ones is where the highly expansive, blue is the next expansive. But if you plot on these soils, there are gypsum locations. You will see there are a lot of expansive soils have gypsum in them. So most of the time, expansive soils are stabilized with lime and cement. So those stabilizations actually react with the gypsum and form ettringite, which actually makes the heaving worse, because that gypsum and the lime reaction leads to ettringite, which I'll show you how it works, causes much more heaving. In Texas, where we have this a lot of work, and there are many locations where identified where there are sulfates. So this will tell us that when we are building the low volume road to moderate or high volume roads, we will know what stabilization one should focus on. You can't just go with the same type of treatment, because that will cause some of these man-made sulfate heaving problems. So we want them to be very careful in the way screening the soils before they select appropriate stabilization. So these are the types of sulfates. So what you see on the right-hand side of the picture is gypsum, which is again calcium sulfate. Then you have other sulfates, sodium and magnesium, which are more soluble than gypsum. But if you look at this gypsum, this looks like a crystals, they shine. They are the ones that actually, when they, when you treat with the soil with the lime, like you see the first reaction, hydration of lime, and you have a free calcium ions. And then you have soils have always says alumina silicates. So those alumina will come out as a free alumina. And then if you see the third reaction, which is calcium here, and then you have aluminum, and then you have sulfates in the soil. In the presence of water, it produces this mineral that's this is the one called ettringite. You can see here the 26H2O. The ettringite is known to bulk up or double its original volume. So when any time you have a rain or something in that ettringite formation, that can lead to a huge amount of volume change, which will manifest into heaving on a pavement structure. So on a low volume road, there are not much heavy layers. So this is easily can cause a disruption or like breaking of your upper pavement layers and causes huge amount of distress. Again, this reaction starts when you have a lime treatment or cement treatment at certain pH. This alumina starts coming out, and it's an important ingredient in the formation of ettringite. So with that, again, there's another mineral which most of the time probably also one has to check it. It's called thomsite. Thomsite is worse than ettringite. As you can see at the bottom, this is again thomsite formation reaction. But one good thing is this only can happen when you have very cold conditions. Unfortunately, that means in certain parts of North India, you may have below like around 4 degrees centigrade, and this kind of reaction can happen. The ettringite convert into thomsite. Thomsite is known to be much more expensive than ettringite. So any time you have ettringite or thomsite, other presence of sulfates, one needs to see how we can design the stabilization properly. So this is again a Ettringite mineral structure. It'll give you a good idea on like how the mineral structure looks like. You can actually qualitatively assess them from X-ray diffraction or SEM imagery. So there's a ways to detect this thing, as a part of a forensic investigation. So this is a nice picture, like a schematic created by one of my PhD students. So if you have sulfates in the ground and you treat with lime, it causes this red ettringite formations, and then water goes from rain, and you can start seeing this thing starts bulking up. As a result, you can see at the upper surface you have pavements, like in this case is a flexible asphalt pavement, started stripping up because differential heaving causes huge amounts of damage to the road there. And this is a very common phenomena in many regions where you have sulfates in the ground. So we collected several case studies, and these case studies covered so many types of sulfate amounts. You can see on the column number 5th, all sulfate amounts. And then you also have lime and cement dosages that are used in the projects at the roadside. And then there are different types of projects, and then soil types. And then they also listed when the heaving started. So all these things tell you this very difficult to generalize this problem. We kind of know there's certain threshold levels, but you can have a low sulfates, but at the same time, if you have the high clay content, if you have a smaller void space, this ettringite formation and heaving can appear. Again, this is depending on the moisture presence. It can happen very rapidly, sometimes weeks to as long as a months or years. The years, particularly if you have larger voids, it requires large amount of crystal growth. Slowly, it will occupy the whole voids in the soil. Then, once it starts still expanding, then you will start feeling the heaving at the surface. And some of the pictures here, this is one of the famous pictures. One of my collaborator, Les Perrin from Army Corps. So this is the road that's a few months old, and then the whole road that is immediately after construction. When the rain started, then they started seeing this attack. They went back and collected samples, and they actually found out there's a large amount of sulfate in this particular region there. And again, this is, you can see the pockets of white stuff that is again sulfates in that area. And again, when they excavated here, they can see where the sulfate pockets, wherever there's a more amounts of sulfate, started pushing the structure up, and you can see the amount of heaving. This is a few inches, and it's a localized heave. That's another major problem. So if you go and sample it, it's very easily you will miss location where sulfates is present. So you need a lot more sampling of the soil at different locations, and then you can see where this problem is happening. You can't just do 2 or 3 samplings and then testing it for sulfates is not sufficient to understand this heaving. And the other issue is, again, this is another picture right during the mellowing process. Like, when they put the emulsion on the top, you can see small humps like 2-3 inches of heaving started showing up within few days. I think in this case 72 hours or 48 to 72 hours. So you can see these pockets where the heaving is, where the sulfates are there in the soil, and then they stabilize with lime. They were just closing it for during the curing process before they put the next layer. When they came back, they found this heaving. So this type of problem is very well documented in our state highway, Texas DOT, and a lot of other agencies. So they mentioned their nice flow chart they gave where they want you to screen the soils. And important thing is you need to measure the sulfates. There are various ways you can measure sulfates: ASTM, ASTO, TexDot. They all have their own methods. They're all gravimetric, but basically they'll tell you how much parts per millions of sulfates you have. So typically in this work, they said around 3,000 is not a problematic, but anytime you're crossing 3,000, then you will have to do some modifications at the new stabilizers. And our here in the state of Texas, they put 3,000 and 8,000. Anything above 8,000, they consider as a high sulfate. So even some areas with lower than 3,000, you can have a problematic conditions. So it's not a one solution fits for all. I found like where soils have 1,500 to 2,000, they still can have a heaving, sulfate heaving. So this is another stabilization guidance. So if you have less than 3,000, typically it's not an issue, but again around 3 to 8,000, they use different mellowing process and double liming, and and they have some success with these things. Above 8,000 at that time they didn't have it, and we have done a study. I show you briefly those results. So next few slides, I talk about few stabilization methods that work for sulfate soils. So I'll start with one of the few things that really works well is ground granulated blast furnace slag, GGBS we call. This is like one of your iron industries like in a slag material. If you ground them, powder them, you can use them. And this material is actually as a co-additive. You can use this with a low amount of cement, and then they can actually provide a good stabilization of a sulfate soil. And they're shown, the study shown both in UK, and then we ourselves used this in one of our small low volume road in the city of Arlington project. And there are some papers on this topic, and it actually worked well. It's only reason is not very frequently used, is not everywhere we have availability of this material. And also transportation of this material can be expensive. We did try sulfate resistant cement type 2 and type 5 in the soil stabilization. We know this work for concrete productions in sulfate area. We even used it for soils area for stabilizing and then supporting a low volume highways, and it worked pretty reasonably well, mostly because they have a lower amount of alumina that helped in reduced amount of Ettringite, which is helped it. Class F fly ash has a low calcium material. It's actually better than Class C in the case of sulfate heaving. So in that sense, Class F fly ash has worked well, and we have used Class F as a co-additive along with the lime. We reduce the amount of lime what we use in a stabilization project. There are other types of methods which we have mixed results. So they have double lime treatment. What they do in this case is, if you have a sulfate soil, they stabilize it, they leave it for a few days, come back, like you saw one of the pictures. Then at that time, if there's any heaving, they go back, rework the soil. They do another application of lime. That's why they call double lime. And then they actually works very well. In some cases, it actually produced good results for this effectively treating sulfate soils without any heaving. Then you also have what we call lime with mellowing. So mellowing is important process. Before you do curing, you need to leave the lime and make with water and then leave it for certain duration, and then come back and rework the soil. So lime with extended mellowing is also pretty reasonably works well in a sulfate soil condition supporting your roads. Okay. And again, we, that's a lime extended mellowing I'll talk about later. And few other studies that are being done. This is one of my collaborator, Dr. Yaolin E, from again Nanyang Technological University in Singapore. Actually, he uses a lot of what we call is uh, different types of slags, GGBS slag and CS material, which is again from carbide slag. So if you look at it, the soils with the cement treatment has a higher heaving. You can see the swelling, whereas the ones that you used different combinations of CS and GGBS, he has much smaller heaving. It effectively stabilized less than 1%, which is again significantly better stabilization. This paper is in soils and foundation. And again, he did some SEM work again, like as you can see here, like XRD's work as with all these methods actually suppress the amount of your Ettringite peaks, so it was effectively stabilizing it. So we have concluded both from engineering swell testing as well as some XRD diffraction. Also it provided effective treatment. At Texas A&M, we have done, and also at UT Arlington, we have done with geopolymer. With geopolymer is the structure that gives here, like you can see here, and all these colors here. So what we used is M is the monovalent cation. We use potassium. And then we use this G molar ratio of 3, and then water solid is a 3, and then the last one is the water molar amount we use as 1. And we created a metakaolin based geopolymer. So we used metakaolin as our aluminosilicate, and we created a geopolymer that actually worked very well. Before we did it, we tried different combinations, like you can see here with all the different numbers, all different things. The one we really felt is K331, and that is the one that actually provided effective stabilization. As you can see here, K331 is here. So when we use these combinations for our geopolymer production, we found significant strength increase. That's what we are interested. And then we developed this geopolymer, and we use this our stabilization of high sulfate soil. As we did here, like we did then check the sulfate soil with the different sulfating types. Here we have two types of sulfate: low sulfate and high sulfate. As I said, above 8,000 is high sulfate, anything below around 3,000 is a low sulfate. So when we stabilized it with the different things, we found out that all these geopolymer stabilized swellings are much smaller, and except for high sulfates, we have not as effectively stabilized. But moderately sulfates and low sulfates, we were effectively stabilized them without any heaving. So this worked. The geopolymer actually worked very well. And we also checked the strength values, and strength also, we found out they're reasonably well. So all the three types of low sulfate, moderate, and high sulfate, we increased the strength significantly, and it actually provided a good effectiveness, similar to other types of chemical treatment, lime treatment. So we felt like geopolymer has the potential to be used as a effective way of stabilizing sulfate soils. And geopolymer is also considered as a sustainable binder, so because it uses some of the waste materials as ingredients, so it will also provide you some green points with a low carbon footprint. So this is a summary, one of the slides. So based on our results at both at UT Arlington and Texas A&M, we have looked at low sulfates. We created this number based on the Texas highway guidance. We looked at several of these things. So we worked with the GGBFS, sulfate cement, fly ash, and geopolymer. These are all pretty effectively stabilized with the low to moderate sulfate soils. So if that is the one, we have done very nice effective treatment. And again, and high sulfates, which we call them, when sulfate number is more than 8,000 parts per million, we have a concern. So we wanted to stabilize in a different way. And one of the other things they do is remove the sulfate soils and then replace with a better soil, which is not necessarily a good engineering solution. And a lot of these studies were funded by National Science Foundation, Army Corps, and NCHRP, and US Department of Transportation, and many agencies. So one of our project with high sulfates, we did it with the Texas Highways. Texas DOT funded this project. Actually, this is where we looked at lime and fly ash and the extended mellowing. And we concluded that from our study, this actually worked very well. Our location is somewhere here in Sherman area. And, we have published quite a bit on this. And when we presented this information, actually, from our research, ASTO, which is again our American Association of State Highway and Transportation Officials. They chose our research as a showcase poster at TRB, Washington, D.C. in 2018. And again, we have done quite a bit of work afterwards. We published quite a bit. And like again, Taluri has published this paper with us and the ASC Journal. So if you are interested on these topics, we'll be happy to share it. So one of the important things I feel like, uh, uh, this particular conference is also looking at is sustainable binders, sustainable methods. I mean, you can do carbon footprint and you can do different ways of cost analysis, life cycle cost analysis, life cycle sustainability analysis. There is one thing that we do in at our research is we try to look at both environmental impact, resource consumption impact in a much more in a comprehensive way. We look at global warming potential, GWP, acidification, eutrophication. And we also see energy production and also embodied energy, when the material we collected it. We also look at the cost of the treatment. And all these things are considered in a radar chart format. And then the lower the radar chart, the better the sustainability footprint. And just for a comparison with one of the geopolymers with 30% and then 6% lime, if you look at it, right now, this is really geopolymer, even though it's considered sustainable, its initial results is not really showing sustainable, mostly because this material is produced in the lab scale. So manufacturing and then cost of that manufacturing and all these things are very expensive. But as the companies start developing them, there are companies starts the whole thing, you will definitely see some good sustainability benefit. So one of the things I would highly recommend is when anytime we develop any of these stabilizers, are checking for them for both the sake of projects or something. We always need to do a sustainability analysis. So this is one of the analysis which we've been working a lot, quite a bit, and has been used in many ways. So that is something I would suggest strongly we should do that. So with that, I think I have 20 minutes. So just I think may have be going a little bit more, but I would like to conclude my talk with the sulfate heave problem. Again, there's a lot of man-made problems. Particularly if you have high gypsum in the soil, so you must screen the soils as a part of geotechnical investigation to see whether we have sulfates. Try to do a more thorough sampling to figure out if we have sulfate pockets, because that's very important. It's easy to miss them. And then I'd mentioned based on the levels of sulfates, you can choose them low, moderate, and high. For low to moderate, we have a good stabilization method, some cements, and then blast furnace slags, and even co-additive as a lime. I mean, lime and a class of fly ash can be good stabilizers for stabilizing those soils. High sulfates, we found out both lime and fly ash with the mellowing and also with the extended mellowing with the lime has provided, including others also doing a good analysis, good improvements in the lab scale design. But I still think we need to do more field works and see how they're working or not. And again, this is something we have done. On one side, we actually monitored; it showed the good improvements, but more studies definitely needed. But one important thing I want to mention, the last bullet, the last highlighted part is all these things has to be checked with sustainability assessments. It should go beyond just only carbon analysis. It should look at everything, cost and other types of impact on from a sustainability perspective. So it should check both environmental, economics, societal impacts. All those things can be nicely evaluated. That is what is needed, particularly rural roads. It requires this kind of analysis and assessments, because that is something very important to preserve the environment in the rural areas. So I'd like to mention a lot of acknowledgements here, several of them here. The agencies that funded a lot of these projects at our universities. So I want to thank them, and also a lot of colleagues helped me. And as I mentioned, several of my collaborators at the beginning. And there are a few papers on the sulfates. And again, I'll be happy to send it to you. If you are interested, please shoot me an email, anandp@tamu.edu. Again, there are a few other papers. So I've been very, extensively publishing on this topic. And these are some of my sponsor agencies. And again, with their support, which is difficult for us to do this work. I just want to thank them for their support. I also want to thank Texas A&M Civil Engineering Department also for providing me this opportunity to speak to you. So again, with that, I will conclude my presentation. I'll be happy when I may not, because it's a recorded session, but please feel free to email me, and I have questions. I'll be happy to answer. Again, with that, I want to thank again the organizers for giving me this opportunity, and also Professor Raghavan for, from IIT Madras also for instrumental in this talk. And again, I hope the agencies from Indian Rural, government agency and ministry will do a major conference in India. I'll be happy to, contribute more extensively at that time, and hopefully we'll do a lot of synergistic works together. And with that, I'll conclude my presentation. Thank you very much for your time.